This session is titled Developing with Security for Java Embedded Devices, and I'm Hinkman Wong. I'm one of the engineers from the Java Embedded group at Oracle. And we're going to be talking about how security applies to Java embedded devices. First, there's our typical safe harbor statement. All the slides that I'm going to present are for informational purposes only. And here's the agenda. I'm going to go over first an introduction to Java SE Embedded. By a show of hands, how many people have heard of or used Java SE Embedded? Okay. Then I'll go into a little bit more details. It doesn't seem like too many people have been exposed to it. How about Java ME? How many people have used, developed, or heard of Java ME technology, Java Micro Edition? Okay, so I'll spend a little time on the introduction. Seems like there's only a few people that have background in Java ME and Java SE Embedded. Then I'll go over the differences in the programming styles that we have between Java SE Embedded, which is a very, very different environment than you're used to on Java Desktop and Java Server. So we'll talk about those differences and what you can do as best practices. Then I'll go over the security layers and different components, security components of Java SE Embedded, and what's the difference between that and what you find and hear in the news about Java Desktop. And then we'll dive deeper into the two parts that are mainly what Java embedded developers are concerned most about. That's encryption, making sure your data is stored locally in an encrypted format that no prying eyes can get to, and also is transmitted using a secure connection, SSL or HTTPS, to make sure that data, especially for enterprise data, is not being snooped upon or spied upon. Then there's also other security features that I'll be covering in the overview that explain different areas that we make sure are secure in Java SE Embedded. There's future enhancements being made, new features in Java SE Embedded 8, and we'll talk about that. Then I have a demo. I have a small Java embedded device that I'll show later on, and I'll review the points that we covered during the slides. And then I'll open it up for questions and answers. This is a smaller group right now, so if there's any questions along the way, just interrupt me, raise your hand, and I'll answer those since it's an informal setting with this small crowd right now. I should call it an intimate crowd. It's an intimate crowd that we have today. Here's the regular spectrum of Java, and on the left-hand side, a lot of Oracle open world developers are more used to the server world where Java EE runs. That's not the focus here. Instead, if you go down a little bit, there's then the desktop stack, which is Java SE. You see that in the red block in the middle bottom on the left. That spans from servers also, not just Java EE, but you can run Java SE on these big iron servers. On your desktop, of course, but then it goes into the higher end of what's known as embedded. And those embedded devices, it could be consumer devices like the toy that you see, there's a robot, but more likely it's enterprise-grade devices that you see like network routers or multifunction printers, or in healthcare there's the healthcare monitors, medical monitors on a network in the hospital. Or it could be industrial automation where on a factory floor you have all these computing devices that are talking to each other. And that's what we're talking about is Java Embedded. And I mentioned before Java ME. Java ME continues the spectrum even lower than that. The thing about Java SE is we keep one full API set, but if you wanted to subset down the API and the spec, then we have Java ME, which tries to have a trade-off between the footprint that's required and the spec that it adheres to. So there's a smaller set of features that are found in Java ME, and that's more for the consumer market like Blu-ray players and cell phones, especially feature phones on the mobile side. And there's extra APIs for changing a channel or fast-forwarding or rewinding a video, for instance, in Blu-ray. So you see those extra red blocks that are on top of Java ME. And then MSA is the mobile services architecture, and that's for doing things like dialing your phone or sending an SMS text message. Those are extra Java APIs that do that. We're not talking about that because in Java SE Embedded, as you can see, we keep that full set of APIs, or the full spec compliance that you see in the lower middle red block under Java SE. And then that's the part right in the middle there, the embedded, that we'll be talking about in this discussion. And as the bullet items for Java SE embedded, we see that I'm pointing out here the differences that we have between Java SE embedded and Java SE desktop. You still get that, well, this is something that's the same. You still get that proven and stable platform that you get with Java SE. So it's the same implementation, except there's, I'll talk about the differences in what we do to optimize for the embedded world and embedded environments. But the APIs are the same. There's a huge developer base. So if you go online and you're scratching your head over a problem in your application, you can find forum groups and discussion groups of talking about Java SE programming. There's also rapid application development. There's all the IDEs, Eclipse and JDeveloper and NetBeans that are out there that help you program in Java SE. And of course, you get the greatness of Java, and that's why you're here at the conference, is you get the fully object-oriented programming environment. You get a virtual machine that takes your bytecodes and runs it. So if you have a jar file, that's going to run the same on any Java SE virtual machine. You don't have to recompile. And then there's memory management, of course, with Java. As you know, being here at a Java conference, there's no need to figure out what you're doing with C pointers and your memory, making sure to free the memory after you use it. And that's big in embedded world because many embedded developers are used to programming in C and C++. So they're already ingrained with trying to remember to do all their memory management. Coming over to Java is just a breath of fresh air. And then there's portability. We make sure to have our virtual machines run on the typical embedded CPUs, and OS is not the desktop OS. On desktop, you see Windows is primarily the OS, and the x86-based Intel chips are the environment that you see there. And then you see Mac OS. We have Java SE, the runtime for Mac OS, and Linux also. But that's really the three ports that you're concerned with in Java SE. In Java SE embedded, we are concerned with many, many more devices, many more operating systems, many more CPUs. It's dominated right now by ARM, so we primarily focus on Linux ARM, not Windows, because Linux and ARM are by far the two features of an embedded device that far outnumber everything else right now. And there's cross-platform issues that we make sure to take care of in our Java SE embedded library so that you don't have to worry about that. You just have to worry about writing a Java program, and that program will run on a multifunction printer with Linux ARM and also on a healthcare device with Linux ARM. It just will, we give the promise of the write once, run anywhere on embedded devices, which is much, much harder to do when you're talking about all the different CPUs and operating systems. Even within Linux, there's different distros that are slightly different flavors and different settings from kernel to kernel. So we do all the heavy lifting for you, and then you just worry about Java code and the Java program that you're programming to. And then there's also, on the hardware side, these CPUs from ARM, as you see in the news, are now multi-core. And that makes it very interesting because our Java layer and our virtual machine, in order to run in a highly optimized fashion and as fast as possible on these new embedded devices, need to be multi-core aware, need to be multi-threaded, need to handle those that multi-processing device. So that type of support is built into Java SE embedded also as a platform. And then you get the security, which we'll talk about in depth in this presentation, and then networking also. So all the ideas that you get from Java EE or Java SE that you know about in Java apply directly to Java SE embedded. As a side note, in Java ME, there's all this, a lot of pain in terms of trying to remember which subset is being used in which part of Java ME, or which APIs are missing, so you have to use some other set of APIs or write your own. That was a pain for a lot of people in Java ME, but in Java SE embedded, what we do is keep that full specification from Java SE So you don't have to make the mental switch going back and forth of what subset you're using. Also, there's a different I/O system called Generic Connection Framework in Java ME. So there was this whole mind shift of how you were programming, how you're using your APIs when going down to Java ME. So we heard our developers and that pain of trying to remember to switch gears when they go from Java SE to Java ME. And now this is why we came out with Java SE Embedded, which is applying your knowledge of Java to these smaller devices. And this just goes over what I've talked about before. The full spec is covered in Java SE Embedded, but we make sure to go in and tweak the libraries and the virtual machine to make sure that there's memory optimizations. It's not using up all 256 meg of your embedded device, of the RAM that's available on your embedded device. And that's because we very much focus on the availability of your RAM as opposed to desktop and even laptops where there might be 4 gigabytes of RAM available, and you don't think twice as a Java programmer when you're in that environment. But when you have 256 or even 128 megs of RAM on your embedded device, that's a big concern, and we address it right away in the libraries. So your platform itself is not churning and using up all your memory before even your application is running. And so that's a big deal with our runtime implementation, is making sure that even the platform is performing correctly for the limited and restricted amount of memory you have in an embedded device. And then there's also smaller persistent ROM and disk requirements so that you can have a smaller footprint, or when you install your application and you install the Java runtime on your embedded device, it's not taking up all the flash memory or all the ROM that you have available. And then, of course, that means your RAM is going to have less impact also, just because when you load in our Java VM and libraries, that footprint that's taken up by the storage space for our VM is not going to be used when it all loads into memory. So we care about the static footprint because it impacts the dynamic footprint later on when you're running. And then there's things to speed up parts of our Java library that we've done. And many years over the past, I come from the Java ME CDC group, where we learned, hey, there's Java libraries that do things inefficiently. Let's go ahead and go into each part of the library and make sure it's running efficiently for small devices. And we've carried over those type of optimizations into Java SE Embedded also. Where is it used? So these types of devices are embedded devices. They're fixed assets, or things that don't normally move around with you. A cell phone, for instance, someone will put it in their pocket and then take it from place to place. But a multifunction printer or a network router, it's just going to stay in one physical location usually. Maybe in healthcare, it moves around a little bit from patient room to patient room, but usually there's less of that intermittent connections that you have to the network and power issues that you normally see in mobile devices. So in embedded devices that we're talking about for small embedded devices, that's one of the areas is in industrial automation. You also have on the factory floor fixed assets where these embedded processors are running in certain stations along the assembly line. One thing that's very common nowadays is to still network these embedded devices, but using a wireless network. For instance, Amazon has their Amazon Kindle. They piggyback on the Sprint 3G network, and then they call it WhisperNet, even though it's still using the underlying protocol and an underlying carrier from Sprint. Just because Sprint has this extra bandwidth, and they said, hey, if anyone wants to contract out and hop onto our bandwidth, then you can set up machine-to-machine communication where these Amazon Kindles are talking to the Amazon data center, getting the latest update of the OS, and being able to pull it over the Sprint network. So nowadays, you could contract out with these carriers and say, hey, I want to use a little bit of your extra bandwidth. So can I have a private network where my wireless network can be set up across the country, across the world? And so that's a big deal because these small devices are now plugged into the regular internet, and not just a local area network. And then there's another distinguishing feature of embedded devices in this talk is that they have small screens or they're completely headless. So you have these small LCD panels that you find in multifunction printers. That's not going to let you see the entire document that you have. It's going to let you push buttons that show up on your screen or touch for a status, a small error message window. So that's very limited in terms of UI that you have on these embedded devices. Also, for input, you're limited to either a keypad, and usually that's a numeric keypad or just a limited set of alphabet letters and numbers on a screen. Or you have a touch screen, which is, again, that smaller LCD panel that you're going to touch, and especially on buttons and menus, and not really a full keyboard. So that's something to keep in mind when you're programming to Java Embedded. Now let's go into the topic of today's talk, which is security. And security is an overloaded term. It can mean many things in terms of Java. Mainly for this scope of the security that we're talking about in this presentation, it's addressing the security in these embedded devices that we want to focus on for this talk. In other talks, they talk about Java EE security or Java SE security. Mainly, we're concerned about the memory use that's happening on these embedded devices. And also you have these lower power CPUs. So you might have a CPU that's running 270 megahertz, not these 3.3 gigahertz quad-core 8-way multiprocessors that you find on desktops nowadays. This is much more limited in terms of what you can do in processing. And then less memory means that you have less area to do your security algorithms. So if you're doing encryption, a lot of times if you do the brute force way of just using AES on Java SE, you're saying, hey, I'm just going to use the latest encryption technology, latest encryption algorithms, and just be able to be safe and in knowing that it's going to be fully encrypted. But then there's a second dimension here when you're talking about Java Embedded is how much memory is it going to use. So you're not just blindly using APIs from security anymore. You're concerned about the processing area or the amount of limited memory you're going to take up with that security algorithm. And then limited CPUs means there's less processing power also for those algorithms. That means it takes more time. So you're going to try to encrypt a string that you normally just do on Java SE and don't think about twice. It just returns right away after you encrypt it. It's going to be a significant impact if you're going to go on an ARM CPU instead of one of these quad-core 3.3 gigahertz Intel processors on a desktop. So you have to keep that in mind, is how fast is your embedded application going to run. And by taking all that in your mind and keeping that as in the back of your mind as something to watch out for memory and for limited CPU power, then you're going to take a look at what Java SE security has to offer. And there's 3 components that provide a comprehensive solution for secure embedded programming that you want. Especially if you're using networks like the internet, where you're hopping onto Sprint's 3G network or some other wider area network. The first component is runtime security. So you want to make sure the behavior is being enforced by the Java runtime that you get. The Java platform is going to watch and monitor. Can you do this action? Can you open up a file on your local hard drive? Can you go ahead and make a network connection to some back-end server across the internet? That is being monitored and managed by the security layer in Java. And then we want to make sure that the application can run safely in a restricted environment. So in this limited memory and this limited CPU, can we still ensure that nobody's snooping, nobody's spying on the memory, and nobody's getting to the data that your embedded application is running? So that's very important when we're talking about healthcare, when we're talking about industrial automation, enterprise, is making sure that all the data during the runtime is secure. Then there's security libraries. We want to make sure that everybody gets the typical APIs that they're used to using for cryptography and for things like encryption and key storage and certificate signing. And there's standard APIs in our Java SE embedded for things like the crypto package that you find in any computer language. There's also the public key infrastructure, which is PKI, which allows you to have a pluggable set of security encryption algorithms. Then there's authentication. How does the user who's on that embedded device authenticate themselves and prove their identity? There's also policy and secure communication in our libraries to make sure that you as a Java programmer can easily say, hey, make sure to protect my files on my hard drive. So I'm going to set this API to say, don't allow the user to touch any of these special files, or don't allow the user to override any settings that I have. And there's also secure communication, where going back to your data center, especially for enterprise data, you want to encrypt it so that there's nobody snooping on the internet and nobody being able to pry into your data as it's going across the network, across the internet. And then it's very important in our libraries to make it pluggable. So it's very flexible, where you can have a new algorithm that comes along, a better encryption model that you hear about. You can buy that, be able to plug it into our framework, our Java Cryptography Extension Framework, or JCE. And this allows you to extend it into the future. And then we have tools that make it more convenient for you as a developer to do things like certificate signing, to do things like taking your jar files and making sure those are protected. There's the key tool for certificate signing, jar signer, and the policy tool that we provide in the JDK. So here's a diagram of what's happening in runtime security. So when we're diving deeper into this, on an embedded device especially, you would have your applications with Class A and Class B, for instance, on the very top. Those are the blue boxes. How can you ensure that on that embedded device, which it might not have a human monitoring all the time like a server might have in a data center, how can you ensure that when it's accessing things, data and files on your device, is it going to be protected? Well, what we have is the orange blocks that you see on this diagram. That's the Java platform. Java SE Embedded has all these class libraries that are following a strict security policy management paradigm. And what we do, as you can see, the Class A and Class B are your application files, or it might be a third party's application. They talk to our Java platform, our orange blocks here, such as file input stream. File input stream in Java allows you to open up a local file. That, in turn, doesn't go right to the file and let you have it. It goes first through a security manager in the middle there in the orange block. And that security manager is going to, in turn, use an access controller and a policy to make sure that it's going to read off in this green block to the right here, the authorization data, or what you as the application programmer or the device manufacturer, what you're saying, this is allowable for this application, this class from some third party is going to be able to open up the preferences file for a user, for instance, and nothing else, but I grant that developer using this class the permission to go ahead and open up that file. And so going through all these steps are a requirement for the Java platform. You go through a security manager. It checks to make sure that the policy file says you're allowed to do this as a certain application, and then open up that file. And so this is runtime security. And again, let me know if there's any questions along the way. Next, we have our security and security manager and policy that we can talk about more in depth. It's something that you, as the device manufacturer or device developer, can set. So there might be times where you want to open up things like user preferences on a device. There's times when you want to keep it completely closed, like a network router or a smart grid device like a concentrator or a smart meter. There's no reason why you would put third-party applications there it would be your own in-house application developers that create a smart grid or a smart meter application. So you might want to shut it all down and have no permissions at all for any other classes than the system classes. Then there's, so that allows you flexibility of defining your environment for embedded device. There's also Java Cryptography extension. And that component, again, that's a framework to allow you to do different encryption algorithms. So when you're scrambling up your data, JCE is the part of Java SE embedded security that allows you to make sure that your data is protected against prying eyes. Then there's PKI, which I discussed before. The public key infrastructure is a big component within Java SE security. And that enables you to have an encryption exchange between on an unsecure public network, such as the internet, and be able to use an asymmetric way of doing cryptography, which means there's a digital certificate that's floating around out in the public there on the internet, and there's no secret key, so there's no way for someone to try to open up your embedded device, find that secret key, and be able to pry and be able to look at and spy on all your encrypted data on other devices. Instead, there's a digital certificate using PKI way of doing encryption that allows you to have that digital certificate be authorized by a authority or certificate authority or a CA in your root set of certificates. And that's a much, much cleaner way and a safer way of doing encryption so that no one's going to break your code. And so that's one big component within security is PKI. It's an entire infrastructure to allow you to do public key or asymmetric way of doing encryption. And then next is JAAS, which is the Java Authentication and Authorization Service. This allows you to give a password and a username and say, hey, I'm this person, and then go off to a backend server and validate that you are indeed the right person to use that device. Then there's Java Secure Socket Extension, which is JSSE, and that again is using the standard for HTTPS, which when you go to a website like Amazon and you want to give your credit card information and other personal information, you want to make sure that it's scrambled along the way. So HTTPS is the web services and web protocol way of keeping a secure connection. And also there's SSL if you're doing, instead of Telnet, if you SSH your connection into your device, you want to be able to type commands and look at results using SSH rather than having, and that's a secure socket layer or SSL that's protecting it, having it inside that pipe that's protected against prying eyes rather than FTP or Telnet, which is open for anyone snooping on the internet and knowing your IP address, being able to see what you're typing on that device. So JSSE is very important for doing the HTTPS and SSL way of protecting your connections. And there's also some optional pieces that are not as popular and not as frequently used. There's Java GSS API that's a generic secure services API that you can use for authentication. There's Kerberos, again, that's for logging into a device. Some people use a standard called Kerberos where they can connect up their corporate passwords and usernames so that it's available to all the devices too. There's Java SASL, which is a simple authentication service layer, and that again allows you to do logins. XML signature, so instead of digitally signing a jar file, which represents your application, and letting that run on your device, you can digitally sign XML, which is all scrambled up, and be able to have the client or the service that gets that XML that's been signed and be able to decrypt it by just the information that's inside the XML. So that's important too if you're going to heavily rely on XML going back and forth between your device and your back-end data center. And then there's tools that, again, that come along with development on the development side for doing security on Java SE embedded devices. Then there's, oh, it must be 12 o'clock. There's the test of the sirens that they do at 12 o'clock here in San Francisco. I think it's for tsunami warnings that they actually do that for. They set that up. But well, anyway, that's just a side note there. Here's a diagram of Java SE Embedded Security Manager and Policy. Diving a little deeper in this diagram, you have your local or remote code up on top. Wants to go ahead and run on your embedded device. And that's the security policy that determines, you as the developer, you'll write out and say, hey, I want this local code to be able to have full access to all my files. Or I want this remote code, the opposite, to be limited to just a sandbox. So in that security policy, it's going to be the input into the Java platform judging whether the local code or remote code, depending on where it's from, gets to play in the full access area or goes over to the sandbox and gets protected. And once that code goes into one of the two blue boxes that are on top there, it has different levels of security because it in turn will go down into the security manager and say, hey, I'm part of the code that has full access. You can also have more fine-grained control of that. And you see those little bubbles there, the blue bubble, red bubble, and green bubble. Those are domains, which means there's even smaller sets of code, such as writing to a file instead of reading to a file, that are defined by domain according to a class, the file writer class, for instance. That domain is going to have a specific policy that you can fine-grain define in your policy file and say, I want all local code, local applications to be able to write to files. That's the blue box. But over in the purple box on the right-hand side, I'll say anything that's remotely downloaded from the internet, I don't want it to write at all. I'll just let it read the file instead. And so you have this really fine-grained set of dials and buttons to control in terms of what the security protection is of your device. And then you have the security managers watching all of this, and that's the layer that protects your applications from your resources or allows certain actions to happen on your resources. And that's at the very bottom. On an embedded device, it's not like your typical desktop system. It's got maybe a SD card, it's got some flash memory, it's got some connections to the internet. And that's really what you want to protect, because you don't want somebody to come in and take over your device and start spamming or sending spam mails or using your device to spy on you. So that's the very bottom box is your private data that is kept secure. Any questions about this? Okay. So now we have, there's also domains, as I was talking about in the last diagram, is an instance of the security policy. So you have up top the two bullets are security manager, which I talked about. That's what's in control. The security policy, that's how you define the limits of the security manager as a developer. And then domains, as a little bit more detail, it's the instances of your policy. So what you've put in as lines of permission, and it also is the place where you define specific access for different areas of code. So for instance, there's the file APIs in your library. That's being protected by a domain. And it can be controlled depending on where the application comes from. If it's a digitally signed application, it's going to have full access to do everything in that domain. But if the domain is protecting against remote code, then it'll look to see up the stack where an application came from, and it might be from a URL that's outside the device, and that would be restricted from using the file system. So that's domains using the security manager defined with a security policy. Now here's a data flow diagram of everything, all the components that we just talked about happening on a Java platform. So we don't have to go over everything, but it's just showing that in a Java SE embedded device, there's a lot going on in the libraries on the platform to make sure your data is protected. There's the purple box up top is for authentication, is for logging in. There's things that will protect your code, like JCE, being able to encrypt it. And then there's sub boxes that you get that will do things in a specific standard, like Kerberos. Or there's PKCS 11, which is the pluggable way of doing different algorithms. What's interesting to note for embedded devices, I'll point out in this diagram, is the bottom here where it says PKCS 11. That is a set of interfaces or a set of standards that allow you to plug in how your cryptography happens. So again, on these limited devices where you might have a 270 megahertz ARM chip, that's not powerful enough to let you run in Java an encryption algorithm, like doing the full scrambling of entire data set. So what you want is something faster, and to do that faster, you can use the standard called PKCS 11 and plug in something specific to your embedded device. So maybe you've got a special ARM chip that can do crypto acceleration on that chip, on the board, on the target board. That PKCS 11 structure lets you do that, lets you do, for instance, the AES encryption. If you say, hey, I'm going to do Java AES encryption, it's going to natively figure out, hey, there's a chip here that I can accelerate on this embedded device. So chip manufacturers and target board manufacturers, this is great because you can have developers write in Java still, and under the covers, it can be really fast on your device compared to all these other devices that are just interpreting Java to do the encryption. And you can make that a selling point. You can say, hey, there's value in my embedded board because you can do encryption a lot faster. And encryption, because you're at this talk, you know that it's very important in terms of embedded devices nowadays on that wide internet. Or you can have other interfaces to PKCS 11. You can have smart cards. So you might have a smart card reader where it would only decrypt the data if you're the smart meter guy and you plug in your smart card into the device, and then you're able to download the data. But if you're just somebody walking off the street up to a smart meter and you want to read this house's information, you can't do it because it's not going to be able to decrypt other than using that smart card technology. So that's another way of ensuring that there's an extra level of encryption for your embedded device. And that's, again, it follows the PKCS 11 plugin architecture, which makes it very easy for Java developers to just say, hey, encrypt this data set. I don't know what you're doing under the covers, but I'm assuming that it's going to be fast and it's going to be something reliable. And that's what we set up, is to make sure that it's flexible in a Java platform to do that. Now, let's dive deeper into JCE, which I mentioned before, the Java Cryptography extensions. And that is in itself a pluggable cryptographic API, and that's supporting a wide variety of services, not just doing the PKCS style of encryption. It's doing things like message digest, where you can hash up and make sure that your compressed files are haven't been tampered with. It can do things like digital signatures so that only signed applications on your device will be able to run, nothing else. And that's important because you've seen security threat information on regular Java SE for desktop is open to all kinds of applications. So there's all kinds of rogue applications out there that are able to get onto our Java platform on desktop because it's a plugin in a browser. If you accidentally go to a URL and there's a applet there that hasn't been signed, it's still going to run and it's going to do something bad. And that's where mainly you see security holes nowadays, is you see it on desktop or laptops or the Mac using that entryway of a rogue application. There's no signing, no checking of signatures, and then it just it runs and finds one of the holes that it can get to your data. Here on an embedded device, if you digitally sign all your applications and you know if a third party or a developer is going to want to run their application on your device, you can say you are required to digitally sign your application. and only run signed applications on your device, you've shut out all the security holes that have been in the news recently, just because any rogue application won't be able to sign themselves to run on your device. There's also bulk encryption. So again, if you're doing data, if you're shipping off data back to your Oracle database on the back end, you want to be able to use JCE to do that, and if you're a Java programmer, you can do that very easily. There's stream encryption. So if you open up a video stream or just a continuous data stream, that is also secure and protected against people spying on it. What we talked about before, the public key infrastructure, that's an asymmetric encryption. And then there's also password-based encryption, where it's not using a certificate. You're just typing in a password to scramble up some data. And there's keys that are being generated and being stored, so that is during the exchange is being handled by JCE. There's message authentication codes, and there's also random number generation. And that's all under JCE, which is a common set of APIs from device to device where your Java programmers can easily pick up and be able to program to. So that's why with the benefits of Java is that you just have to remember JCE to be able to program to your embedded device. There's also cryptographic services implemented to the standard, so that if you go to RSA or if you go to some vendor, like even an open source provider like Bouncy Castle, they're going to create a standard that plugs into JCE. So they're going to say, hey, use my open source encryption, because at Bouncy Castle, I've written to JCE. And so you would download the jar file, and it would have all the interfaces implemented to JCE. And that means that you have implementation independence. You can use our providers for our security encryption algorithms from Oracle, formerly from Sun. And then you can also use Bouncy Castle, an open source version. You can go to RSA. You can go to VeriSign. You can use anybody's implementation because it's adhering to JCE. And then there's implementation interoperability, which means that you can mix and match. You can mix Bouncy Castle and Oracle's encryption together in JCE. And algorithm extensibility. So if there's a brand new elliptical algorithm that comes out and your device was baked before that happened, you can still use JCE to allow that algorithm to get flashed and updated to your devices and be able to use that new style of encryption. And here's JCE in action. Here's your application again is on the top. It's going to figure out, hey, I want to use MD5 for message digest encryption. And then it goes through the provider framework, which is the key part of JCE to make it pluggable. And then it goes and figures out which one of the MD5 implementations you want. And that's provider dependent. So on the very bottom, you see 3 different providers in those green boxes there. There's provider A, provider B, and provider C. That they all have different types of algorithms. They might have SHA-1 and SHA-256. Provider B might have a MD5 there and a SHA-512. And there's a provider C also has an MD5 encryption algorithm, and then maybe SHA-256. You can decide, hey, I want to use provider B's way of doing MD5. And then it goes through and tries to check where MD5 is available, and then you say, hey, I wanted to use provider B. Then the provider framework does all the heavy lifting and figures that all out for you, and then returns back to your application, hey, I gave you an encryption algorithm to use. It's an implementation that's using the ARM chips version of encryption, so go ahead and do that on your embedded device. So that's what JCE does as a provider framework that's pluggable. Then we have the options for JCE. We have a provider that we provide from Oracle. And I guess that's why I'm saying Sun, because we call it Sun PKCS11 JCE provider. And that's supported on Solaris, Linux, and Windows. So those are from Oracle, what our implementations are natively of fast, secure encryption algorithms that you can use by default with your JDK. Then there's Sun MSC, which is the Microsoft Cryptography API JCE provider, and that's only supported on Windows. So there's an optimized way of doing it that's found in the Windows operating system that we allow you to use. Then there's the Oracle uCrypto JCE provider, and that's natively written on Solaris Spark and Solaris x86, and that allows you to do cryptography in an optimized fashion on Solaris servers. So those are different providers. Just like in the previous slide, you can request, hey, I want to use an encryption algorithm from this specific provider, depending on where you are, what kind of platform you're on. And so now here's the Sun PKC S11 that we provide as an implementation of encryption algorithms. This allows Java applications to access the PKC S11 implementations that we talked about, that it might be your hardware layer doing this encryption acceleration and using the encryption on a chip to do your calculations and your algorithms. It's using a cryptographic token interface standard that's across the board. You can find the standard in the C programming language, in Python, and other programming languages, and we're providing the Java interfaces to do the same thing. And this is provided by RSA Security, so that anything that's done natively in terms of doing fast encryption is an interface using the standard, using tokens under the standard, so that you can have your hardware cryptography take place, for instance, or you can have smart cards do the encryption for you, encrypt and decrypt. The Sun PKCS11 provider is supported, again, for Solaris Spark and x86, on Linux x86, and on 32-bit and 64-bit Java processes. So it's also on 32-bit Windows x86. There's going to be an early access for 64-bit Windows support later on in JDK 8. And then for the Microsoft part, if you wanted to have Windows support on a Windows machine, and this might be interesting as Windows 8 gets ported to ARM devices like tablets. So for embedded world, you might want to take advantage of the Sun MSC API provider where you can use Microsoft's crypto instead. And then there's all kinds of other hardware vendors that can provide crypto services that we talked about, and you could plug these as hardware modules onto your device. And here's the Solaris one. So if you're working with embedded software on a big Solaris server, you can use the Oracle uCrypto provider, and that's optimized for the Spark T4 if you're familiar with our Spark architecture. That's a hardware-assisted cryptography acceleration, so that allows you to do the encryption in a very, very fast way on servers. And this is only available on Solaris. So you get the picture of all this optional ways of doing security because it's a plug-in framework that you get in JCE. And so in the future, for Java SE Embedded 8, we have PKCS11 for 64-bit Windows, not just 32-bit. There's going to be crypto operations over the network, so you can use hardware that's available on your network instead of on your device itself. There's going to be more encryption algorithms, more cipher suites, more message digests, stronger, better, faster, all kinds of things. Good stuff coming in Java SE Embedded 8. And now here's a fun part. Here's a demo. So I'm going to switch over to my laptop. So can I have also this mic? Thank you. I think this one. Okay, that's on. Thank you very much. I'm going to switch our windows over here to show first NetBeans. How many people in the room have used NetBeans as an IDE? Okay. So I don't know. How many people have used JDeveloper? No. Okay. So NetBeans is I like NetBeans. I've switched over completely as my editor. I used to use Emacs and XEmacs as my editor, which kind of dates me because that goes back to to the 80s. That was a big editor then. But now in NetBeans, I find it so much easier to use all the context type of helps that they have. Like if you're typing along and you decide that you need some help with what the different methods are, you can go ahead and use their type ahead feature and being able to pop up a menu of different selections that you have. Now it's not going to work. Oh, that's dot. Yeah, there you go. Thank you. And you know, just having this at the touch of your fingers and having the Java doc be available, that's really cool. So I never had this when using Emacs, and then type ahead feature saves me a lot of typing, which is hard sometimes when you're typing out longer method names. But what I'm going to show you here is a crypto sample demo. And it's using the typical Java SE crypto packages that you find. So any IDE that can program in Java SE, you can program for Java SE Embedded. And that's the great part of Java SE Embedded, is that there's no special spec for Java ME that you have to look for. And then here, we're just going to take a string. We're going to take the string, hello, this is a test. And we're going to encrypt it and decrypt it. And then we're going to use this current time millis to time it before and after. And so here's a couple key parts of the code. It's very easy to do encryption. You get your key generator and say, I want to use one of the security algorithms that are in my provider. In Sun PKCS that I talked about before, there's AES. And I want to init it to 128-bit encryption, and that's it. You're going to be able to generate your key, and then you're going to take that key and use it to do your encryption and decryption. So here's the key. This step right here is important for embedded developers because, as I said, as an embedded developer versus a desktop or server developer, you are worried about memory and about processing time. And this, under the covers, is going to take up the bulk of the time. So you have to be aware of that, hey, this is a big deal to do generate key. It's going to go off and churn a lot on an ARM chip. On a desktop, you won't even flinch. You won't even notice that it's doing that. But in embedded, again, this is the topic of the talk, is you have to worry about each line of your code. What is it doing in terms of memory? How much time is it going to take to process? And you have to just be aware from experience that that's going to take a lot of time on an embedded device. And then you just go ahead and say, I'm going to do encryption using AES, and then you'll take your source string, which is that hello world, and be able to do final. Do final, I always thought that was misnamed. It should just say encrypt or decrypt. But that's what it's really doing, is taking the mode of your cipher and doing it, performing it on a set of bytes from your source string, which is the hello, this is a test. And then I just print out what it looks like after it gets encrypted. And then I do the opposite. I'm going to put it into decrypt mode over here. And then I'm going to say do final and decrypt it and then show it afterward. And then to wrap it up, I'll just show that how long it takes on desktop and how long it takes on embedded. Any questions about this demo, about this program? I like the colors that it does, syntax highlighting that it does in the IDE too. It really pops it out when I've missed a semicolon or I mistyped something. It really does help a lot. So let's go ahead and go on to my Windows machine. If you look at the printout of the CPU info, this is a pretty hefty machine here. It's got an i5 Intel, 2.6 gigahertz, and let's count 1, 2, 3, 4 cores on it. So it's pretty hefty type of laptop machine. And I'll go ahead and run that program that I just did. And you can see it only took 198 milliseconds. That's down here. It's taking that source string, hello, this is a test. It turns into an encrypted set of data, which is hex data that you see here. And so you send this over the internet and nobody's going to be able to break it. Then you're going to be able to decrypt it because you know what the password is to decrypt it on the other side. and that's going to be 198 milliseconds. So let's just make sure that's around what we get. That's 180 milliseconds, 180 milliseconds. Oh, okay, so let's call it 183 milliseconds as the average there, because it seemed to be hovering around there. Now let's switch over. I'm going to hold this up. This is a Beagleboard, and this is a Linux ARM device. So this, I call it a poor man's Raspberry Pi, even though it costs more. It's like $300, and a Raspberry Pi is like $99. But you might have heard in the show people talking about embedded devices such as the Raspberry Pi. It makes computing on embedded devices a lot cheaper nowadays. The low end is $49, and I think there's a Raspberry Pi that's comparable to this device that's $99. So you could buy this and program for these embedded devices nowadays at a very cost-effective way using these test development boards. And it's connected with a serial cable to my laptop, and that's all I'm doing. I've loaded on here Java SE for Linux ARM, and that's a big deal now because we're providing it from our group as a download. You can just go to the Oracle website, say I want the binary to run Java SE 7 on this real tiny device, and just get our binary, run it the same way you would run as you saw on a Windows box. So now let's go on to the Beagleboard, and I'm going to switch over to this. Oh, of course, the demo gods need me to reboot here, so it's because I moved it around, that's why. Okay, so and it just takes a couple seconds to reboot here. So I could talk about it while it's rebooting. You can see there's nothing up my sleeves. There's no sleight of hand here. This is an actual Beagleboard running. It's booting up Linux. It's only got 256 megabytes. Its CPU is an ARM chip, as I talked about, and that means it only has, I think, a 700 megahertz chip on it. It's more hefty than I was talking about in the presentation. It's got more than just the 270 megahertz that some real tiny types of chips have on it. But now it's into the login. Here you can see it's Angstrom. Angstrom is a Linux distro that's very common on embedded devices nowadays, and it's a Debian-based Linux, so it's very familiar to a lot of people that have used Linux on desktops. And so I'm going to go ahead and just to show that this is a embedded device, not trying to fool you with my other device. Here it is, ARM chip, 720 megahertz, and it's called the Beagleboard here. And then I'm going to go ahead and run that same program that I ran before. And there it is. So it finished up in 2.8 seconds. And I'll run it again just to make sure that I'm going to get the average and not just the first time it runs. So, you know, it was 2.8 seconds, 2.7 seconds, 2.6 seconds on an embedded device. What took 183 milliseconds on my laptop. So something that you can't even tell is happening on a laptop is all of a sudden something in terms of usability. Let me get rid of that. In terms of usability, that's a big deal. Oops, wait a minute, sample, sorry about that, demo 1. It's a big deal that you have to wait 2.7 seconds for it to come back. So that, again, if you go back to the code, that bulk of the 2.7 seconds is coming from here. And this is going to be, as an embedded developer, you're going to just know that, hey, when I do a key generation on an ARM chip, it's a big deal, so I better be aware and be able to program for it so that people know that it might pause there for 2 seconds, 3 seconds before it comes back. So that's what I'm trying to point out in a demo, that it's not just that you have the same APIs on embedded and desktop. you have to be aware of what's happening under the covers in the memory and in processing. And that really sums up the lesson that for embedded device programming, especially for security. There's all kinds of things happening in the security algorithms that you have to be aware of. And hopefully that helps. I'm going to now go back to the slides and just maybe open it up for just a couple questions if you have any questions. Anybody have any questions about Java embedded or security for devices? No? Okay, well, I'm available also if you want to come up later after the talk. I know it's lunchtime, so you might want to be going off to get your lunch too. But that concludes my talk. Thank you very much. Hope you enjoy the rest of the show.